Hello, my name is Lewis Correa Sanchez and I'm a systems engineer and I am currently studying a master's degree in geoinformatics at the Universidad Distrital Francisco José de Caldas in the city of Bogota. On my part, you will have a strong reading from Colombia. This presentation is about the methodology for the implementation of QoS in Live 5 networks in 5th generation environments.
This article is the result of a research in which the approach, analysis, and implementation of a service quality algorithm was carried out that allowed to improve the performance in UDP traffic in a simulated Li-Fi network with the NS2 tool. Special emphasis was placed on the MAC layer and the physical characteristics of the Li-Fi networks to obtain similar conditions to the real ones. The results were compared with three research documents that allowed establishing the viability of the proposed algorithm. Definition of simulation criteria and tool selection. The simulation criteria established to implement QoS in Li-Fi networks over 5th generation environments are mentioned. Taking into account that the methodology was oriented solely towards the quality of service in terms of Li-Fi networks, it was necessary to delimit the observation framework in items to relate this optical network with 5th generation environments. Definitions. Efficient use of the spectrum. This is evidenced by the efficient use of technologies, as in this case optical frequencies in wireless environments. Second, low latency. The delay in the networks is what is commonly known as latency. One of the fundamental parameters in 5th generation networks will be a very low latency. Third, coverage and perception of service. The most important limitation in Li-Fi networks is the need for line of sight to guarantee the communication process. In the next table, from the point of view of required protocols, the protocols for the transmission of video in streaming mode in real time are of certain relevance for the analysis, being their presence in the configuration parameters of the simulation tool to a certain extent necessary for get an approximation as close as possible to reality. Tools and observations. First, UNet Riverbed. It requires a license and does not allow modification of libraries and protocols. It has a high learning time, but its robustness makes it very reliable. Second, NS2 does not require licensing. It has an enthusiastic support community, and it allows modification of protocols and changes in models from the coding point of view. It's very agile. It is reliable and highly used by the academic community. UNet++ does not require licensing. It is reliable and highly used by the academic community. Modular configuration and programming based on C++. Fourth, STNet requires license. It has a short learning time but does not allow modification of libraries. Methodology. The first phase of the project consisted in determining the metrics and QoS services. Within the Li-Fi environment, a fundamental aspect should be included, such as the 802.15.7 standard, corresponding to short-range wireless optical communications through the use of visible light. The importance of the physical layers and control of access to the medium of this standard is that these layers determine the maximum transmission speed of audio and video that can be achieved while the lighting characteristics are not affected. The standard mentions three types of physical layers with different combinations of digital modulation and coding schemes. This information allowed us to establish a starting point with respect to transmission speeds, taking into account that the development of this work was focused on Li-Fi networks from the user's point of view regarding the possible 5th generation environments that may apply. Definition of QoS metrics and services. The metrics chosen for the analysis according to the specific objectives were the following: latency, packet loss, and bandwidth. The analysis of the set of these metrics allowed to identify the perception of the end user with respect to the services in real time mentioned above. The QoS services that were validated in the development of the project should be those that require graded network characteristics for the end users. With respect to QoS, the following processes were taken into account for the treatment of real-time traffic in the Li-Fi network. A. Marking and classification. B. Policing and dropping. C. Queuing and scheduling. D. Shaping. E. Post-queuing. In the flow diagram, the general QoS application algorithm for Li-Fi networks is shown, taking into account the specific policies of load management and queue management. This decision is oriented to that thanks to the high speeds that are handled in optical communications, it is possible to increase the processes of quality of service that will obviously result in increases in processing times. However, this will be compensated with the high transmission speeds. Algorithm. Starting from the flow diagram of the previous section, we proceeded to design a new algorithm that would allow to establish QoS on optical media, in this case, Li-Fi networks. This with respect to the latency, packet loss, and bandwidth metrics. This new algorithm relied on the development of mathematical modeling based on the interaction of each of the components involved in the communication process. Following considerations were taken into account. Components: transmitter, receiver, and media. All these elements are optical and open air respectively. Descriptive variables: latency, packet loss, and bandwidth. QoS metrics: identification of interaction rules. Packages must pass a marking and classification process to prioritize services. Privileged, privileged processing rules should be assigned according to the identified service. Subsequently, policing, dropping, and queuing processes must be executed to improve the perception of services in real time by the users. Descriptive parameters of the interactions. The interactions between the aforementioned processes and the market packets are given by the characteristics of the Li-Fi network. From the point of view of bandwidth, latency, and packet loss, in addition to the layer of liaison and physics, the latter described in detail in standard 802.15.7. The proposed algorithm, which is a variation of LAQ, will be called optical low latency queuing, or LLQ, for Li-Fi network environments, modifies the token bucket mechanism for the treatment of real-time traffic in inclusive conditions for the standard 802.15.7. For purposes of the OLL algorithm, the following classes of service shall be taken into account for the purposes of multimedia traffic in Li-Fi networks. Service for real-time applications with packet sizes and constant arrivals. Service for real-time applications with constant packet sizes and variable arrivals. Service for real-time applications with packet sizes and variable arrivals. Finally, best effort service for applications that are not in real time and do not require QoS guarantees. Once the package is classified, the metrics that will apply for the optical token bucket processes are calculated. These metrics are associated with the maximum and minimum average bandwidth, the size of the packets, and the information associated with the service class defined in the previous step. Simulation in MATLAB. In the simulation on the left, traditional packet token with A, 50 interactions, B, 100 interactions, C, 500 interactions. In the simulation on the right, optical token bucket interactions with A, 50 interactions, B, 100 iterations, and C, 500 iterations. Li-Fi networks allow the implementation of complex algorithms that guarantee QoS as a bucket token, disregarded by other networks due to the time they required for processing. The differentiated handling of packages through duplicate token bucket allows a better management of the resources of the system, since the packages will not remain longer than necessary, and the flow of them through the Li-Fi interfaces compensates for the times that are invested in the diff serves process. While it is true that the performance of the network is 38% from the point of view of the network bandwidth, with the quality assurance proposed in this work, the quality of the link increases because the packet failure disappears due to collision effects. The packet loss for the proposed solution is very low, allowing to obtain a packet delivery rate to the 99.8% interface, taking into account the administration of congestion in an appropriate way, ensuring the correct management of resources within the elements of the network. You can find me at LCORREAS at CORREO dot UDISTRITAL dot edu.co.